All right, what's up, everyone? We are live. We are doing a Leetcode challenge today, so super excited to dig right into this. I'm going to go ahead and make sure that we are actually coming through on the stream, and then we're going to get right in. If you are just joining me, we're doing Leetcode contest 274, and I'm going to just be working through some of these problems, and we can feel free to try and solve them along with me. I want to show you what my thought process is, the way that I approach these problems, and give you a sense for that. So let me just pull this up and make sure that we are streaming, and then we'll get into it. All right, Facebook is working, and YouTube, maybe. All right, looks like YouTube is working too. So feel free in the chat if you have any questions or anything that you're wondering as we go through this, go ahead and drop those in the chat, and we'll go ahead and jump right into this contest here. So again, what we're doing here, and let me share my screen. Thanks, Abhishek, for confirming that it is in fact working, and you can see. Again, all right, so you should see my screen here, and this is what we're doing. We're doing Leetcode weekly contest 270. In fact, working. So my goal here is really to all right, so you should see my screen here, and this is what we're doing. To see like what my process is for solving these problems. So these are not problems that I've done before, and we're just going to jump right in and see if we can solve them. So honestly, let's just go ahead and start with the first problem here. All right, in this problem, and I'll make this a little bit bigger so that hopefully people can see it a little better. All right, given a string S consisting of only the characters A and B, return true if every A appears before every B in the string, otherwise return false. Okay, so in this case, we have A, and then we have B, and so that is true. In this case, it's false. I mean, so essentially, you know, one way to think about this is that we're essentially saying, like, is the string sorted or not? Another way to think about it would be, is there any pair of characters that is like not in the right order, right? Because in this case, it's not really that difficult for us to, you know, we only have two types of characters, so we only have to compare the two. And then it's not a question of whether the entire thing is or I guess it is a question of whether the entire thing is in order. But really, it seems like the easiest way to do this is just going to be to check every pair of characters. If we check every pair of characters, we can say, okay, in this case, A and B is correct, but we get to here, and this pair is incorrect. There's a B before an A, and so that is not going to be valid. So in a problem like this, coding this up should be fairly easy because we have a linear time solution here, right? We can basically iterate through the string and check all the pairs. Now, is there a way that we could do this any faster than that? Probably not, right? Because at minimum, we're gonna have to go through the entire string. If we considered like a counter example here, let's say that I had this, let's say I had like this string here, and I had an A at the end. Then in a case like this, we could try basically, like let's say that we didn't look at these last two characters and we only looked at all the remaining characters in the string. Then we would find that this is valid even though it's not actually valid. And this could be anywhere. Like this kind of inversion, quote unquote, could be anywhere in the string. So without looking at the entire string, we don't know for certain. And the point is really that we have to go through the whole string to make sure that this is valid, right? Like there's not a way that we can do this reasonably in sublinear time. So with that in mind, I think our solution's pretty good of just checking for those inversions. And so let's just iterate through our string. So for int I equals 0, I is less than s dot length minus 1, I plus plus. Basically, we're going to look at each character and the following character, and we're going to see, are they basically in sorted order or not? And this should be really easy for us to do because all we have to really do is just say if s dot char at I is greater than s dot char at I plus 1, then that's going to be false, right? That's an inversion. And otherwise, we're going to return true. Right? We're just checking each pair, whether that pair is correct. So what we would get here is we would see like, okay, B is greater than A, which makes our string invalid. And so it would return false. And otherwise, we're returning true. We run this. All right, we got the right answer. Let's submit it. So that all worked. And now I guess I kind of need to zoom out here a little bit so that we can see. Where did we fall in this? I mean, this is an interesting case where it's like, okay, there's not really a big difference between the runtimes. Like all of these are so fast because it's a fairly easy thing to solve. So, you know, this variance here doesn't really mean anything. That's kind of interesting compared to some of these problems where there's like a massive variation. Okay, I'm a little curious what people were doing to get that memory down, but like we're in a place where I'm not really worried about it. So okay, that one was pretty straightforward here. So let's go ahead and move on to the second one. And I guess actually before we move on to the second one, just to go back to this one for a sec, I think this is a case where when you're thinking about a problem, it really comes down to understanding what it is that is actually being asked. Right? This sounds so basic, but if you really understand what the question is, if you understand what the kind of like what the definition of that solution is, like what is a valid solution, if you really take the time to understand that, it's like it becomes a lot easier. Because yeah, we could do something where, okay, we're going to check are all the A's in front of all the B's, because that's how the problem is defined, right? But we don't need to do that, right? We don't need to check are all the A's in front of all the B's, even though we could. Like we could basically iterate through and say, and this might be a approach that we could take. We could iterate through and basically say, I'm going to check is everything A, and if it's not A, then it becomes B. And then once I get to a B, I should only see B's from there to the end. Right? I could do something like that. That's actually going to be a slightly slower solution on average because we have to iterate through the whole string every time, potentially. So, there's a lot of different ways that we could approach this, but really understanding what the problem is clearly makes it really easy for us to solve a problem like this. Abhishek said, what if the string can have a series of characters like, so like if the question was multiple characters, I mean, you would have to be more careful, right? Because you would not be able to just check for individual inversions. If we go back to this problem, let's say that we don't just have the characters A and B, but we have any character. So we could potentially have, A, B. I'm trying to think of what a counterexample might be to this. I guess you are always going to have an inversion somewhere, right? You're always going to have some case. So yeah, this probably would work actually if we had a string that was any number of characters where it's just like, we're basically saying, is something in sorted order? And by comparing every pair, we can determine whether something is in sorted order or not. Right? In terms of, really that's all we're doing is we're determining, is this string in sorted order? And you only need to compare the values that are directly next to each other. Because really, for something to be in sorted order, for every value, the next value has to be greater than or equal to that value. Right? Like that's basically how we define it. At any time that's not the case, then it's not going to be in sorted order. So yeah, this same basic process would work with any number of different characters. All right, so our second problem here, number of laser beams in a bank. So anti-theft security devices are activated inside a bank. You're given a zero index binary string array representing the floor plan of the bank, which is an m by n matrix. Okay, so it's basically like, yeah, it's like this. And zero means that the cell is empty, while 1 means that the cell has a security device. There's one laser beam between any two security devices if both conditions are two devices are located on two different rows and for each row, there is no security device in the ith row. Laser beams are independent. i.e. one beam does not interfere with or join with another. Return the total number of laser beams in the bank. Okay, so basically we have, so basically they're going to connect from one row to the next row, right? Each laser beam, it can't connect across rows. So essentially what they're saying is we have the two devices are located on two different rows, so they can't connect across one row. And there are no security devices in the rows between them. So for example, this one in row 1, and I can't really highlight this or anything. I think you guys can see my mouse. This one in row 1 here cannot connect to like this one in the last row. And so let's think about, and then in this case, none of them connect at all because they are all in the same row. Right, so essentially what we have is that for each row where there are laser beams, they all connect to all the ones in the next row. So like in this case, we have 3 in this row and 2 in this row, which means that we have 3 times 2 different connections, right? Because all 3 of these ones in the first row connect to all 2 in the second row. So if we count them, we get 1, 2, 3, 4, 5, 6, which makes sense. And then in this other example, we have these 2 on row 3, and we have 1 on row 4, and so they both connect, so you get 2 times 1 or 2. And in terms of the total number, we can just count those up. So really, if we reduce this problem down, let's think about like what we're actually doing here. So our rows look like this. And I'm gonna split these into multiple so that we can see what it actually looks like. So basically, we're looking at, are there ones in a given row? And if there are ones in a given row, then the number of ones in that row times the number of ones in the next row that has ones in it becomes the number of beams between those two rows. And so essentially what we can do is we can just count this up, right? Like we can iterate through our rows and say, okay, well, if there are ones in this row, and then there are no ones in this row, so we just skip it. And then we basically find the next row that has ones in it, and we multiply them, and then we repeat that process until we get to the end. Right? And so if we think about this from a coding standpoint, what we're really going to do is just iterate through our rows. And I'm thinking I might want to write some quick function that will help me count the number of zeros. So let's call it num0 or num1s, or I guess we could call it num lasers. It's not really lasers, I guess it's security devices. We can just call it num1s. And we'll just count the number of ones in the string, right? So right, so we'll just do that, and then we'll return our. So that way we can easily get the number in each row. Or, in each row. And now all we have to do is we have to iterate through the rows, right? And so what we'll do to do that is we basically need to, and one way to, what we might want to do is, I guess that's not even really necessary. So I'll call it num beams equals 0, and then for we might even want to do like a while loop here. I don't know. I'm kind of debating what the easiest way to actually code this up is going to be, because we basically want to find that first row, and then we want to iterate to the next row, and then we want to update our like starting row to be that second row and keep iterating from there. So we kind of have this like stagger stepping like iteration. And let's do a for loop. So we'll say for I equals 0, I is less than bank.length I plus plus, and then we'll just do, so if num, well, let's say, so that we don't have to calculate it multiple times, we'll say num1s equals num1s bank I, and then basically if this is not 0, we want to find the next one, right? So we'll say for int j equals I plus 1, j is less than bank.length j plus plus. I'll call it right. So if the row 1 count is greater than 0, then we're going to find that next row if it exists. So int row 2 count equals num1s bank j. And so basically what we want to do is if this one is greater than 0, so if row 2 count is greater than 0, then we need to do a couple things, right? So first, we want to add the number to our result. So we'll say numBeams plus equals row 1 count times row 2 count. And then we also want to update our I, right? Because I becomes j, basically. Or I becomes j. Now, because we're incrementing this, it really, I becomes j minus 1. So I equals, I believe, see, this is where it's like it might make more sense to do a while loop because the incrementation gets kind of weird here. We'll have to double check that that's correct. And then what happens when we get to the end? So we're basically going to, for the last one, we would iterate through here and we would never find it. So yeah, we would just drop out and then return numBeams. Okay, so that obviously didn't work. So let's debug here. Let's what I'm really wondering is what are the indices when we meet in the middle here? And are those correct? Okay, so we didn't, let's see if this is, all right, so why is this? So we're not, I mean, obviously this is not working properly. let's just try that. I mean, it seems silly, but so why is that not working? Oh, tough. That would be why. See, I mean, and I've talked about this in a couple streams before, but like the debugging part is really just about being strategic about what you're doing, right? Like there's so much of debugging these things is just figuring out like what is going on and like where am I going wrong essentially. And if you can do that, then it's going to make your life a whole lot easier. Because a lot of times I see people just trying to like fix random stuff in their code and hoping that it's going to work. And honestly, it doesn't usually work. So it's good to take the time to really understand like figure out, okay, what is it, where is it that this could be going wrong? And then figure out, okay, how do I fix that thing? Or like, how do I print stuff out so that I understand where it's going wrong and then go from there? So I'm going to check this, and what I really want to see is which rows are we adding, which rows are we adding to our result? So we had 0 and 2, and then 1 and 3. Yeah, so this is not right. This should be, so I think, this is really ugly, but I think that we just need to, because we basically want to reset it. Is this working? Because essentially what's happening is the j, we want I, the next value of I, to be what j was. But what's happening is that that's getting incremented and j is getting incremented. So, and this is being weird, so let's try. Oh, I see. That actually broke it because looks like we're running into infinite loop here. So I mean, like honestly, the better way to do this would be with like a while loop. So we'll just call it int first equals. And then while and basically I'm just going to move all this into there. So I'm going to say here row and count, and then inside this I'll do while. I'll say basically second equals first plus 1, and while second is less than bank.length. And then we're going to do this whole thing. So it becomes so if it's equal, we do this, and then we say that we can basically do first equals second, and then break out of this inner while loop. We could do second minus 1 and then do we're not incrementing second here. See, this is the one downside, is that it's really easy when you do the while loop instead to run into like a a case like this. So, okay. But basically what we need is we need to like, again, we're doing that stagger step. So it's just a little awkward to code up, but this should work, I believe. Yep, okay. That was fun, a little bit of debugging there. Okay, we're a little slow here, but I mean, in terms of the actual complexity of our solution, you know, this may not be the most efficient way to do it, but we are still running in, let's go back to the actually, we can see our code there, right? Yeah, so in this case, what is the complexity of this? Well, the complexity of our code here is basically linear, right? Because, well, it's linear, and then for each of the strings, we have to compute it. And so I think someone said, yeah, we could just keep one count rather than redoing the count each time. There are, again, a lot of ways that we could probably make this a little bit more efficient. But from a complexity standpoint, this is totally fine. Yeah, it's a little slower, but I think there's a lot of times where I'm like, okay, our space usage is relatively efficient here. I'm not too worried about it as long as it's running, you know, efficiently from a time complexity standpoint. Thank you. Yes, the complexity for this one is going to be n times m, right? Because we have the complexity of going through the whole string, and then we have the complexity for each iteration. We have to go through the rows. So it's going to be dependent on the length, on the total number of rows, and it's going to be dependent on the length of each row. All right, let's maybe do, I don't know. Do you guys like me trying to do all of them? I feel like it goes on for a really long time because we can also just stick to maybe today we'll just do 3 and then we'll keep this a little more concise. Because I feel like these have a tendency to drag on pretty long. We'll see how we feel after this one. All right, so you're given an integer mass in which represents the original mass of a planet, and you're given an integer array asteroids where asteroids I is the mass of the ith asteroid. You can arrange for planets to collide with asteroids in an arbitrary order. If the mass of the planet is greater than or equal to the mass of the asteroid, then the asteroid is destroyed and the planet gains the mass. Otherwise, the planet is destroyed. Return true if all asteroids can be destroyed. Otherwise, return false. Okay. So basically, we have, when we collide with a small asteroid, we gain mass, and when we collide with a large asteroid, we can be destroyed. So if we ran this planet into an asteroid of size 21, we would be destroyed. If we ran it into this 19, we would be destroyed. But if we do, like, you know, in this case, 10, 9, 19, what was it? Yeah, 19. So, oh, and if they're the same size, that's okay. I see. So, you know, my initial thought here is there are a couple things that we could do. One is that we could try all the different orderings, right? We could try just doing lots of different orderings of planets. And if we did something like that, we might be able to do some sort of like dynamic programming, because we would be able to basically do the different orders and then cache them. The one downside is that that doesn't really work super well when we are removing these planets, because it's like, okay, if we've already hit that asteroid and we can't hit it again, then we have to be updating that as we go, which makes it really hard for us to do dynamic programming. We saw a similar issue with that on a problem that we did on the stream maybe last week or the week before, where it really didn't, even though, you know, on the surface it looked like maybe we could do dynamic programming, it wasn't actually something that we were able to do. So my other thought with this is there some sort of greedy approach that we can take? because my initial thought is that like the fastest or the best way for us to do this is going to be for us to just the one way that is always going to work is going to be to just destroy asteroids in order of increasing size, right? Because if we destroy asteroids in order of increasing size, basically that would mean 10 would destroy 3 and become 13. 13 would destroy 5 and become 18. 18 would destroy 9 and become 27. 27 would destroy 19 and then destroy 21, so that would work. In a case like this, 5 would destroy 4 and become 9. It would destroy 4 again and become 13. That would destroy 9. But then, you know, to destroy this 23, we basically have to get together as much mass as we can to destroy the planet. And so by going in increasing order, we are always, as we get to larger planets, we are always maximizing the amount of mass that we can have when we get to that point. And that's going to be not necessarily the only way to be successful, but if that doesn't work, then no other way is going to work, because any other way, then we would have less mass when we tried to destroy a given asteroid. So, I mean, in all honesty, this seems like this should be pretty straightforward if we think about it that way, because all we really need to do is just sort the asteroids and then do a count through, right? So, like, if we think about how we code this up, I'm going to do like arrays.sort asteroids. And like doing this is going to be a complexity of n log n, right? Because we're just going to sort it and then we're going to linearly iterate through it. So I'll basically say for int I equals 0, I is less than asteroids.length, I plus plus, and I just check, right? Like, and I guess actually this is kind of similar to that one that we did earlier where we're not going to iterate to the end because we're comparing to. It's similar to that first problem that we did. So we'll say, basically, if well, I mean, we can maybe start with the first one. So if mass is less than asteroids 0. Do I really need to do this? Okay, never mind. I take this back. So we'll do it like this. It's just going to be if mass is less than asteroids 0 I, then return false, right? Because we destroyed the planet. Otherwise, mass plus equals asteroids I, right? We're just going to add that to the total mass. And then at the end, if we make it through the whole thing, we return true. And I'm pretty sure that's all we need to do. These are interesting. These contests are interesting because some of the problems are like, I think a lot of the problems are much more about your kind of parsing what's happening than necessarily being super tricky. So we might do some other, we might try some other things rather than just doing these contests, like doing some practice problems and stuff. Okay, so what happened here? I'm gonna guess that this was a matter of out of bounds exception. Just based on the size of the input, like I don't know if people remember this happened to us last week where it was like we should have used a long basically. So let's try doing that and see if that helps. So let's do long total mass, and then we'll just sub this in here. Yep. Yeah, so when we have that really big input, I mean, those are annoying because it's like, it's hard to tell what's going on. You're definitely not going to do it by hand. But I think what we saw in the last week one as well is that, you know, if we passed everything else up to that large input size, and this is kind of a good just note in general, if we fail a test case because the input size is huge, then chances are it's some sort of overflow. Because otherwise, they're not usually putting some weird tricky thing in some massive input. At least on Leetcode, they're not. So just, something that you can keep in mind as you're doing this is that makes your life a lot easier. All right, we are, kind of within the distribution here. We are, yeah, I mean, I guess, like, I'm trying to think, I wonder if there's a way that we could make this significantly more efficient. I mean, we are, like, our time is being slowed down by sorting this. So the question is really, could we do this without sorting in a way that would be efficient? And, potentially we could, maybe use some sort of other data structure or something. We could also do like a partitioning thing. Like if we wanted to get really fancy, what we could do is rather than sorting the whole array, we really just need to partition it into like sections that are larger or smaller than a given amount, right? Because if we partitioned it, we could basically say let's just add in all of the asteroids that are smaller than the current size of the planet. And then we would have some remainder, we could partition that and continue on. So like there might be ways that we could make this more efficient, but I mean, again, this is not like it's not a slow solution, so I'm not really upset about it. All right, 3 down, and yeah, let's at least take a look at this one. We'll see how long it takes, because again, I don't want this stream to go on forever here, but. And again, if anyone has any questions or anything you want me to clarify, go ahead and drop those. You can go ahead and drop those in the chat as well, and I'm happy to talk through anything. All right, so maximum employees to be invited to a meeting. Company is organizing a meeting and has a list of N employees waiting to be invited. We have arranged for a large circular table capable of seating any number. The employees are numbered 0 through N-1. Each has a favorite person, and they will attend the meeting only if they can sit next to their favorite person at the table. Favorite person is not themselves. Given a 0 indexed array, where favorite I denotes the person's favorite person, return the maximum number of employees that can be invited to the meeting. Okay. So in this case, yeah, like everyone wants to sit next to person 2. So we're kind of limited here because only 2 people can sit next to person 2. All the employees cannot be invited. Yep. Note that the company can also invite 1, 2, and 3 and give them their desired seats. In this case, where everyone's favorite is a different person, then we can invite more. In this case, yeah, all right. So let's think about this, because in a basic, the simplest way for us to start, or like my immediate thought is, okay, where do we end up with a contradiction here? And the first contradiction that I think obviously comes up is that if more than 2 people want to sit next to anyone, then they're inherently, someone's going to be excluded, right? Not everyone's going to be able to attend because only 2 people can sit next to any other person. Now, that also can have a downstream effect, right? And that's where I think this gets a little more tricky because, and let me switch over to the iPad here because I want to draw this out. All right, so like what we could have happen is, let's say that person 3 wants to sit next to 1 person, or let's say, I don't know, how do we do this? So, okay, like let's look at the example that they gave us. So the example that they gave us was 3, 0, 1, 4, 1. So based on that initial thing that what we initially said, this seems like it should be okay because there's only two people who want to sit next to any one person. But if we actually start drawing it out, and let me put the indices here. What we end up with, like, let's start filling this in. We have our table, and then we get, let's say, we'll put person 0 here, 3 here, 3 wants to sit next to 4, so it would be 4 here. And now what we end up with is we'll put 1 here, 2 here, and now we have a contradiction, right? Because 1 wanted to sit next to 0. And we can't sit 1 next to 0 because there are 2 other people who want to sit next to 1. So this is the sort of thing that we're dealing with. And roughly speaking, when you see something like this, my immediate thought, and I guess I should have left those there, 0, 1, 2, 3, 4, is when we look at the definition of this problem, we have 2 things. We have data points, which are the employee numbers, and then we have connections between those data points and other data points, which are basically telling us that we have a graph here, right? We have the employees and we have who they are connected to. And when we think about it in that way, we can start to draw this out as a graph. So let's draw out our data points first. 1, 2, 3, 4. And then the edges of the graph become those connections. So person 0 wants to sit next to person 3. So they connect to person 3. Now person 1 wants to sit next to person 0. So we get this edge here. Person 2 wants to sit next to person 1. Person 3 wants to sit next to person 4. And person 4 wants to sit next to person 1. And so with this, we can determine, okay, well, is there a valid way to do this? Or we want to determine, is there a valid way to do this? And essentially, the issue that we run into when you look at this is that, like, let's look at this graph and just think about it at a high level. Because let's see if we can come up with a way to translate this into, like, to think about how we would solve for this. So in this case, what I'm seeing is that most of this looks fine because person 0, I'll use a different color here. Person 0 can sit next to person 1 and person 3. Person 4 can sit next to person 1 and person 3. But where we end up with an issue is here, right? Because we end up with this issue that person 1 has 3 people who are trying to sit next to them. Like, they're trying to sit next to someone, and 2 other people are trying to sit next to them. So basically what we end up with is we end up with 3 edges here, right? We end up with 3 connections where there are 3 people who, for this to be valid, should be sitting next to person 1. And at max, we can have 2 because there can only be 2 people sitting next to any person. And so if we think about, like, solving this, well, the obvious answer when we visually look at it is that we could remove, we want to probably remove the person with the fewest dependencies because that'll make our lives easiest. So we would basically just remove 2 here. And that, once we remove 2, now this is valid again. Let's look at another example because it'll help us, I think, clarify kind of what this looks like from a graph perspective. And because we're still trying to figure out, like, what exactly is it that we are going to do, right? And so our first example was 2, 2, 1, 2. And our graph, so it's 0, 1, 2, 3. Our graph becomes 1, 2, 3. 0 points to 2. 1 points to 2. 2 points to 1. And 3 points to 2. So essentially, when we're looking at this, really any of these that we would remove would, actually no, that's not true, right? Not any one. We can't remove the 1. Because if we remove the 1, then 2 can no longer sit next to 1, right? And so in terms of doing this, it becomes a question of, in this case, obviously we can remove the 0 or we can remove the 3. Now, let me see here. Now, in terms of how do we actually solve this? So essentially, again, like the total number of edges between nodes needs to be maximum 2, right? We can't have more than 2 edges between any node. The one kind of exception here that we do have to deal with is if we have something like this, with the 2 pointing to the 1 and the 1 pointing to the 2, that basically counts as a single edge. So arguably we can have single directional and bidirectional edges. But the question that we still have to figure out is like, how do we remove nodes to get to a point where this is going to be valid? Right? Because we understand now kind of what the conditions are that we need to meet. And so in doing this, we can come up with some sort of, like, if we have this, we could write a function that would basically say, is this state valid or not? Right? Is this a valid way for us to or like, is this a valid combination of people, right? By looking at the graph, it allows us, and that's the nice thing about this graph, is it becomes fairly easy for us to, we just really count the edges between the nodes. And the question becomes then, like, again, so how do we figure out what the, so we could write some function that would basically validate this. They would say, like, this state is valid. But how do we know whether, how do we get to there? And I would look at this as, this is probably like a searching problem, right? Because essentially we have a state and we can tell whether we are at it, and we can tell whether our state is the desired state or not. We have an initial starting condition and we have that ending condition. So what this really probably looks like is, let's try doing a binary search, or not a binary search, a breadth first search. So in this example, let's say we had our graph where it was like, 0, 1, 2, 3. We had the edges like this. And this basically becomes one state. And then all the other states that we can get to are states that we get to by removing a node. So we could start by removing the 0 node, and we would get, something like this. We could also try removing the 1 node, which actually we probably wouldn't do, because we would just say, okay, if we remove the 1 node, then it's still going to be because I guess we could remove the 1 and the 2 node technically. So I mean, let's just say for argument's sake that we remove the 1 node, so we end up with like this, and then we kind of end up with this like dangling pointer here that is something that we would have to, which would make this invalid. And then we would end up removing the 2 and the 3, right? And so if we did that, then essentially we get to all these neighboring states. And if we get to a neighboring state that's still not valid, then we say, okay, well, let's remove another node. And we can basically repeat this process. And effectively what you're doing when you do this is we are doing a search and we are finding all of the possible neighboring states. And it's going to give us what is that shortest path. And the shortest path we are finding by removing 1 node at a time. So the shortest path, or the length of that shortest path, is this question that we had originally, which is what are the basically what are the minimum people that we need to exclude from the meeting to make it valid, which is, essentially that it's just the inverse of what it is that we're trying to compute. And so with all that, let's switch back over to Leetcode here, and let's start coding a few things up here. Let's think about, what was this actual, all right, it's just a graph like this. So how do we want to represent this? Because I think that that's kind of where this is going to get a little tricky, and that's where there's going to be a lot of stuff that we kind of need to figure out, is like, how are we representing this? What does our validation process look like? And honestly, I don't necessarily want to code up this whole thing now, because it's probably going to take us a while to code everything up. But let's start thinking about at least some pieces of this. So we could do, for example, what I like to do is basically a hash map of like integer to, so it's a hash map of integer to set of integers. And so let's create a function that's going to basically construct our graph. And what is this going to do? Well, we're going to say, or this doesn't need to be a hash map, but and then we're going to add all of our favorites to this, right? And so to do that, we'll say for int I equals 0, I is less than, and actually this doesn't need to be a full, these don't need to be sets, right? Because each one only maps to 1. So it could just be this. So let's do it like this, and then I is less than, and the reason that I'm doing this as a map is that I'd like to be able to actually remove values. And I'd like to be able to basically remove the keys and then say, is that still in the, like basically if something points to, I'd like to be able to find it easier like dangling. But now that I'm thinking about it, I'm not sure we even need to do that. We could track, like, we could basically have a Boolean array that's like which ones are still in the. So okay, let's actually try this. So So we'll assume is basically is attending is going to be like which of the people are attending are currently going to the meeting. And so what I can do, let's basically check whether this is valid or not. And so there are a couple things we need to do. So we need to make sure no one's neighbor is not attending, right? Because if someone wants to sit next to someone who's not attending the meeting, then it's not valid. Then we need to make sure that no one has to sit next to more than 2 people, basically. Those are like the 2 things, right, that we need to check for. And so, I mean, honestly, I'm not gonna worry for the moment about how efficient this is. I'm just gonna try and implement something. So to make sure that no one's neighbor is not attending, we'll say for int I equals 0, I is less than 1, I plus plus. And basically we'll say if not is attending, or I guess we need to see is this person attending. So if is attending I, right? If the current person is attending, then is the person that they wanted to sit to next to also attending. So if is attending I and is attending favorite I, then that basically means that we're all good. And so really what we want to do is the opposite of this though, right? Because we want to say it'd be like if is attending I believe that the way that you do it is it's like it's not so what we want to do is if I basically the problem is if I is attending but I's favorite is not attending. So if I is attending and not, but see the problem is that we want to skip it if this is going to return false if I is not attending, which is a problem. We'll just break it out. So if is attending I, if not is attending right. So basically we're making sure that everyone can sit next to the person that the person that they want to sit next to is actually there. So that's the first thing. And then the second thing that we need to do is we need to check that no one is trying to sit next to more than 2 people. And so to do that, you know, we can say basically we'll iterate. What I'm gonna do is I'm gonna iterate through each person and check for them. So I'm gonna say so for each person, now I'm basically going to check how many people are they trying to sit next to. So I'm going to int neighbor count equals 0. So let's say if they're pointing to their favorite and their favorite is pointing back to them, then that only counts as 1, like edge. So it's basically if favorite I equals I, then count plus plus. Or actually, you know, what I'm going to say is I'll say that if that's the case, then I'm going to basically skip it. So if this is not equal, then I'm going to go ahead and add an edge. And otherwise, I'm going to count the edge later when I iterate through the remainder. So I'm going to say for int j equals 0, j is less than favorite.length, j plus plus. If I is not equal to j, because we skip it when they're the same one, if right, so basically I'm going to go through and I'm going to count. And then, I mean, here I can just, if and otherwise, I'm going to return true. So what we essentially did here is that we checked all the neighbors. So we checked whether someone's neighbor is, whether the person that someone wants to sit next to is attending. And then we said, okay, for each person, if they're pointing to someone who is not also pointing back to them, then that's one of their slots that are available. And then otherwise, and this should also be, you know, if is attending. Because otherwise we should skip this, right? So if they're attending, then we basically say, so if that would be, if they're not pointing to each other, then that's one edge. And then for everyone else, anyone who is attending and is pointing to us adds an additional edge. And so if there are more than two edges, then it's not valid. Now let's try this, and obviously this is not going to run properly, or it's not going to give us our result, but let's just try, and let's try a couple examples here and see if this actually does what we think it should do. So what are our examples here? Let's try these three. So this was the invalid one. Now the valid one was we removed so I guess we can, I think in this case they said they removed employee 3, right? So let's do, this is gonna be, and then it's new int true, 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 true. So this one should give us false, but then if we make this false, then it should be true, right? So let's try running that. Oh, yep. Oh, oops. Not. All right, great. So we got false and true. Let's just try a couple other examples just to see. So our second example is this. Let me just copy both of these. This one I think should be valid. Right, so we don't need to do 2. Let's try that. That was true. And then let's try our last one. Because once we get this part done, the rest of it's actually going to be easy, relatively speaking. Because this is the like all the logical complexity that we have to deal with. So this is going to be, we need to add an extra. And then we're not inviting employee 2, so. Yep, okay, great. So this seems to be working. So now we just need to do a breadth first search, right? And to do our breadth first search, we're basically just going to try updating all versions of like is attending. And so what that's going to look like is we'll have a queue. That is going to be like to visit. And actually, you know, there's another problem that I did where is a little annoying, but might be a good way to do it for this, is where instead of doing this instead of tracking this as an array, we can track it as a string, because what that's going to allow us to do is it's going to make it it actually makes it a lot easier for us to like manipulate some of this stuff and compare stuff while we're searching. So what we can do is basically we're going to end up with a string where it's like, you know, 1 1 1 1 1, that's going to be all trues, and then it's going to be, if we had 1 1 0 1 or whatever, it's going to be false. So let's actually change this up and let's rewrite this a little bit. So what this becomes is attending a car at I equals 1. And you'll see in a sec why this is going to be way easier. So what we're going to do is then this becomes a string. And you know, we do have to construct the like initial string. So I don't know, there's probably an easier way to do this, but in Java I feel like this is basically the way to do it. And then what we do here is, so our initial becomes to visit dot add sb.to string. And now what we basically want to do is we'll say we're doing breadth first search, so we're going for while not to visit dot is empty. And we are going to basically, so, you know, string cur equals to visit. We're going to get the first value from the queue. and then we're going to basically see, is this valid or not, right? So if is valid favorite and cur, then essentially to get the number of people that we need to remove, we just need to count the number of zeros in our string. So I'll add that. I feel like we don't even. Right, so we just do this, and we num zeros in cur, right? So that's the one case. But then the other case is that we have to basically find all the neighbors, and all the neighbors are just, we try removing each one, like a zero from each position in our string, right? So, and to do this, I'm gonna add another, because manipulating the string is kind of annoying. So, and so basically what I'm going to do is I'm going to convert my string to a string builder, and then I'm going to do SB, and I'm going to basically just take an index and set that value to 0. So SB dot, I think it's set car at, and then it's index 0 and return SB dot to string. So now basically what we do is we're going to iterate through everything. And we'll say, so for int I equals 0, I is less than, so if it's not already 0, we can try setting it to 0. And to do that, we would just do toVisit dot add. What do I call it? Replace with 0. So we're going to do that. We're going to add it. We're going to add all of those to toVisit, and then if we get to the end and we've removed everything, then really we should return. It meant that there was. I mean, we shouldn't get to this point actually. So I'm actually just going to return -1 because. No, wait, that's not true. We could get to this point where we have to basically remove all of them. So return favorite.length, right? Now that's basically what we end up with here. So let's see how many bugs there are in my code. Might be a pen. Line 29. Oh, I see. All right, so we got a result. Are we doing this backwards? Am I doing this backwards? Oh, yeah, I think I am. It's the number of people who can attend the meeting. I was like, this looks like it's the exact inverse. So that means that we just want to count the ones instead. And then this does become 0. That was just my bad. Okay, that time we did get the right answer. Moment of truth, drum roll. Okay. This is going to be a pain in the ass to debug, though. So, like, I mean, in a case like this, we can draw out the graph. I'm probably going to... I don't think I'm going to take the time on stream here to debug this, because you at least have a pretty good idea. Like, there's probably... there might be something slightly wrong with this logic here. I guess what we could do is see what the result was that we ended up with and see if that one's valid. So let's do that, and I'll grab this and... Yeah, so like I think the thing to do here, and actually let's go through this real quick and then we'll wrap, because I just want to, we might be able to deduce something interesting. Who knows? So our array is 1 0 0 2 1 4 7 8 9 6 7 10 8. And that's 1 2 3. And so if we draw out this whole graph, we'll get... We'll try and do it in a big circle, I guess. And so we end up with this. 0 points to 1, and 1 points to 0. 2 points to 0. 3 points to 2. 4 points to 1. 5 points to 4. 6 points to 7. 8 points to 9. Wait. 6 points to 7. 7 points to 8. 8 points to 9. 9 points to 6. 10 points to 10 points to 7. 11 points to 10. 12 points to 8. All right, so I think we can, like, you can see what the issue is here as we look at it, because really the issue that we have is something that we didn't address in our initial kind of, so this looks like this is probably an issue with our actual logic for validating is this correct. Because basically what we have here is we have this entire thing cannot exist. What we have, and the problem that we have here, is that we have a loop, right? And so if we have a loop, then either these are the only people seated at the table, or none of the people seated at the table, right? Like essentially what happens is we're going to have to remove this entire half of the board, because for these to all sit together, they would have to basically, we would have the table and they would have to sit around the entire table for like them to all, for it to all like loop back. And so essentially, you know, as we look at this, this is just something that we would add to our logic around the validating it, right? This becomes slightly more complicated. It's like one more kind of case that we have to handle. But practically speaking, this shouldn't be too difficult for us to deal with. We would probably just want to look for like, you know, if there are, I guess like really what we could look for is just, is there a loop that doesn't include all the like valid values, right? And to determine whether there's a loop, we would have to do some sort of essentially depth first search or breadth first search from each one. Which again, I'm not going to do that now, but shouldn't be super, super hard. So, and once we fix that, I think that the logic on the rest of it, you know, should be totally fine. So yeah, I think those are some interesting problems today. Thank you all for joining me. Just taking a look real quick here if there are any questions. Ruslan said, hi, I have a question. If I can't solve a problem, should I check the solution or need to push myself until I come up with a brute force solution? Yeah, so generally what I recommend for this is don't spend more than like 30 minutes to an hour stuck on a problem. Because if you spend that time stuck on a problem and you're not making progress, it's like spending more time stuck on that problem is not going to magically get you unstuck, right? Like if you are making progress, if you are moving in the right direction, then it's really valuable because it you are getting stronger at doing the thing. So I would say if you are making progress, then, you know, keep working at it. If you're not making any progress, then what you can do is look at the solution, but basically look at the solution and then close it up and try and solve the problem again by yourself. Because it's that process is going to help you to understand, did you understand what you studied? Did it actually, like, did you internalize it, or did it just kind of like make sense when you read it but didn't actually understand it? So that's a really important key, is that you need to make sure that you really do understand it. But yeah, it's definitely like, it's good to push yourself to come up with a solution, but if you're not making any progress, then it's also doesn't make sense to just waste time on that. Vidya, all the problems are linked in the below in the YouTube description. It's Leetcode contest number 274. And with that, I'm going to go ahead and sign off here. Thank you everyone for joining me. Hope everyone found this helpful, and I'll see y'all next week. We'll be here same time, same place.